Okay, so before we get into binary search trees, I want to talk about the homework task 2 a little bit to let you know what to expect from task 2. So task 2, in my opinion, I always have to qualify this with in my opinion or else somebody will call me out on it. But in my opinion is one of, if not the easiest tasks of the semester. It's not objectively easier than like task 1 of homework 1, but you're so much stronger developers at this point. You know Scala a lot better than you did when you did task 1 of homework 1. So it might feel like the easiest one just based on where you are as developers at this point. The biggest challenge with task 2, again, in my opinion, is overthinking it. I do have quite a few students who tend to overthink this one and make it a lot harder than it is. The code that I'm asking you to write isn't all that much. So what I want to do is just let everybody know what this task is actually asking you to do and give some background information on it. So hopefully almost no one overthinks it this semester. Or no one at all would be fantastic. All right. So we're going to write this make decision method. I'm going to jump right to the code to talk about this. We have this make decision method that takes an AI game state and a binary tree node of decision tree value and needs to return an AI action. Now all that sounds like a lot, and you know it is. There's a lot going on behind the scenes. But I want to show you what's going on behind the scenes and separate that from what I'm actually asking you to do. So we want to return an AI action, and by default this just returns move player in a random direction. So this player is going to move in a random direction, and move player extends AI action, so that's a valid action. We could also stop the player. We could fire. Those are the three. Fire, stop, or move are the three actions that an AI player can take, or any player can take. And right now we're just moving in a random direction. And if we go to our server, we can see that we're telling the AI to update every 1 second. So every single second, we're going to ask the AI player what it wants to do, and it's going to choose a random direction and just move in that direction. So when you run the server and you open up your browser, or open up the HTML in your browser, you'll see that every second, the AI is going to pick a random direction, move in that direction, and then a second later, it's going to pick another direction, move in that direction. Not very interesting. And of course, your homework is to give that AI some more decision-making power. So every second, it's going to make a more reasonable decision instead of just moving around randomly and aimlessly. There's a lot of starter code in here, like an actor system, actor of, and props and all this stuff. There's a lot of stuff in here that we used to cover in 116. And for better or worse, I think for better, we don't cover it anymore in 116, but it is still in the handout code. So if anybody's curious how that stuff works, I'd be happy to talk about it in office hours or even after class and stuff, if it's a quick question. But you're not expected to understand that stuff that we don't cover anymore in 116. This specifically the actor system, which is a way of writing concurrent code. I don't want to go too far down this rabbit hole, but just a quick overview. When we briefly saw GUIs earlier in this semester, we had that. We had I forget what it's called, the action timer. We had the action timer, which was called 60 times per second, and that handled all our concurrency, and the GUI handled our concurrency. Concurrency is when you have multiple pieces of code running at the same time. Without a GUI, like this doesn't use a GUI, we have a web server and then a web front end. So without the GUI, we have to build our own concurrency, and we do that with an actor system, which has effectively 3 main loops. 1 to update the game, 1 to send the game state to the players, and then 1 to update the AI, what they're going to do. We have those loops running at different intervals. We also have first order functions. So we actually have functions that we're putting in variables and then calling those functions. This is another thing that we don't cover in 116 anymore. With actors, concurrency, and functions, it was just a bit much, and we were leaving students behind and then not having enough time to cover the topics well, the ones that we really need you to understand. We couldn't cover those well enough, like OOP, for example. But if you want to know how first-order functions work, you don't have to, but if you want to, feel free to look through the code. But if you're looking through the code and you get to this point and you say, what the hell is that? Don't panic. Just kind of back away. Just be like, I'm not going to look at that code. And that's perfectly fine. So your code is going to get a binary tree node, the class that we saw on Monday that we created, the structure of a binary tree. This is going to be the root of a decision tree, and its type is going to be decision tree value, which has two methods. And this is the part that you do need to know, is how to call these methods. It'll have two methods, check, which takes an instance of an AI game state, and action, which takes an instance of an AI game state, which is really convenient because you have a reference to an AI game state when this method is called. So you take that AI game state, you shove it into these methods, and that'll determine what you do in your code. So the first thing you'll do is call the check method, which is going to return one of three values, either a negative int, if you need to navigate to the left of this tree, a positive int if you should navigate to the right. I'm doing that backwards. Negative if you should navigate to the left, positive if you should navigate to the right, and if it returns exactly 0, that means that this node is an action node, and then you need to return this action, whatever this action returns. So there's two types of nodes. That's the part you need to understand, is how to call these methods. So understanding that API, how to interact with objects of this type. But underneath the hood, if you are curious about diving deeper, this class is extended by two other classes. Action node, which always returns 0 for check. And then action will call a function and then return whatever action that function returns to determine what's actually going to happen for this node. That means by the time you get to an action node, that means this is the action that the AI player should take, either stop, move, or fire. Or the node could be a decision node, which its check should always return either a negative or positive int. And if everything's working properly or navigating the tree properly, action should never be called on a decision node. A decision node purpose is to tell you whether to go left or right. This is kind of like in the 20 questions example. This would be a question that you ask the player, and then you either navigate left or right depending on the answer, yes or no. And then an action node would be like you're thinking of a dog, would be the analogy to bridge over to that one. In a decision node, check, this is going to be a function that will return negative or positive int. This should never be called, so in your debugging, if you ever see stop player of AI 0, you know something went wrong in the way you're navigating the tree. So you can use that to help you debug if you ever see stop player AI 0. So in your code, wrong one, when you get this game state, you don't have to do anything with the game state itself. All you're doing is taking that reference to a game state and passing it to those two methods that you're calling. You're going to call those methods on the values of the decision tree. And then you're going to use that int that's returned to decide, do I go left? Do I go right? Or is this node the action that the AI is going to take? And what I need to return, the AI action that I'm going to return. So you don't need to crack open the game state. The game state has, by the way, a whole bunch of stuff in it. You don't need to mess around with any of that. Just give it to the decision tree and decide how to navigate the tree. The decision tree itself, so this is how the rest of the game is going to interact with your code. It's going to call this make decision. It's going to generate a decision tree, which is going to be what this method does. This is going to create the three action nodes, whether the player is going to move, fire, or stop. Create those nodes as binary tree nodes. because those were functions. No, those were the nodes, and then putting it in the binary tree. But those take functions, like this here is a function that takes a game state and returns an action. Start building the structure, the nodes of the tree, and then have the decision nodes, which are going to decide how to navigate the tree. And my decision nodes are either going to return +1 or -1 to determine how to move. And they're going to check how far away you are from the closest player. So if the closest player is further than 10 units away, we're just going to stop. We're not going to do anything. The closest player isn't in range of us. If we're in between 5 and 10 of the closest player, this node is we're going to navigate to the move action and hunt down that closest player. And then if we're within 5 units of that closest player, then we're going to shoot at that player. So depending on the distance to the closest player, that's what's going to determine how these AI behave. So it's going to use the code calls all of your methods, puts it all together, finds the closest player, the distance to the closest player, navigates that decision tree. All that stuff's happening with your code. And if it all comes together right, you should be able to run the GUI and see these AI players behave that way. Once you get within 10 units, they'll hunt you down and then start firing at you once they get within 5. There is no required testing for this objective. Because if I required testing, you'd be building all of this, which I hope you agree is pretty complex, especially for a single test case. And then you'd also be building AI game states, giving different game states to your decision tree, and then making sure that you get the expected AI action returned from that, which is what I had to do in my test for Autolab. And I had this decision. Either I make you do that testing, and either I don't make you do that testing, which is obviously the choice I made, and this is one of the easiest tests of the semester, or I make you do that testing, and it's one of the hardest tasks of the semester. Probably the hardest by far, by a pretty wide margin. You have to do all that testing. I decided to go easy on it. There's just a lot going on here. And I didn't enjoy writing those tests. I don't want to put you through all that, because it'd be a lot of tedium, and I don't think it accurately reflects your understanding of binary trees. So I lean towards no on that. But you should still test your code if at an absolute minimum your testing is running the server, opening the HTML, and checking if the AI does what it's supposed to do. At the very least, do that. And maybe run the debugger to see if, well, that'd be a little tough because you'd be in the middle of all this code. But try to see what the AI player is doing, see if it is doing what it's expected, the 10 units, the 5 units, these thresholds, and then try to debug from there. Okay, any questions about the homework before I shift into binary search trees? LOL. Yeah. Like I said, it's one of the easiest, if not the easiest task of the semester. It's one method and no tests. And that method isn't very, like if you really been paying attention this week, including today's lecture, like that method it might take you just a few minutes. Like it can be that simple if you're fully understanding how to navigate these trees. And I think that's okay. I think it's okay to have a task that's a little bit of a break, especially at this point in the semester. I think we're all pretty exhausted. What's the meaning of the parameter f of AI state to int? So that's a function that takes an AI state as a parameter and returns a value of type int. So it's like defining methods, but it's not attached to any class or object. It's strictly an actual function, not a method. So this is a function that takes an AI game state and returns an int, and then we can call that function by the variable name, give it a game state, and then this will return an int and that's what I need to return as an int. So whatever that function returns when I give it an AI game state as an argument, the int that it returns, that's what I'm returning from this method. In functions, especially mixing functions and methods, I'm always careful to say the right thing, whether it's a function or a method. But now it's just methods all the way down in 116. But when there are functions, like we have a function being called from a method, and the difference actually matters. The big difference is a function doesn't have a reference this. The way it's implemented, I don't want to go down this rabbit hole. It actually does have a reference this, but it's a reference to the function itself, which is almost never useful. It doesn't have like state and behavior that you can access through the keyword this. It's a big difference for a function. Any other questions? As I'm moving away from homework, this is your time to, if you're struggling with something on the homework, this is your time to ask. Office hours is your time to ask. But if it's something that pertains to everybody. Okay, moving on. Talk about binary search trees. If, just like last time, so data structures and algorithms used to be learning objective 4, so I renamed all the file names to the slides. So if you click on the slides today and you get light mode slides, just refresh the page and you should get dark mode slides. So if you're looking at light mode slides right now, just refresh, get the updated link where it's LO3 _ 5 _ BST instead of LO4 _ etc. So just so you know, don't burn your eyes on light mode slides. BSTs. BST, I'm going to define the whole thing in one slide. It's right here. A BST, in general, can have any type. It can sort on any type, just like our very versatile sorting methods. In today's lecture, I'm just going to stick with ints and less than as the comparator. So we're going to sort ints with an increasing order, like the default ordering of integers, just so we can focus on binary search trees. And every time I say something, I don't have to say according to the comparator, the order that it defines. Like I'm not going to word things like that. I'm just going to say if it's less than, if it's greater than. Just keeps things simpler. But these are much more versatile than just ints with increasing order sorted. All right, so a binary search tree is a binary tree with a specific property where every single node, for every single node in the tree, every value in its left subtree, which is the tree defined by its left child, so this would be the left child of the root, and then the entire tree defined by that node, if that node were the root of a tree, that whole tree would be the left subtree of the root. So for each value in each node in the tree, every value in its left subtree is less than that value. Every value in its right subtree is greater than that value. If that's true for every single node in the tree, you got yourself a binary search tree, or at least satisfies the properties of a binary search tree. This example is the same tree that I used on Monday because I wanted to foreshadow binary search trees a little bit. That tree that we worked with on Monday did follow the properties of a binary search tree. And this applies to every node, so it applies to 5. All these values are less than 5. All these values are greater than 5. For this node, this value is less than 2, greater than 2, less than 8, greater than 8. So we've satisfied that property for every single node. So we satisfied the property, like this tree satisfies the property of a binary search tree. And then duplicate values, we have to decide how to handle those. The binary search tree concept, like the computer science concept that we're talking about today, doesn't care how you handle duplicates. And you have 3 options. When you actually sit down to write code for a binary search tree, you have 3 options of how to handle duplicates. Depending on your application, you might choose one of these 3. You can either break ties to the left. That's what I do in my implementation that we'll see today in the implementation that's in the repo. So if I insert 5 into this, 5 is going to have to go somewhere over here. In fact, it would have to go right here. You can break ties to the right, or you can not allow duplicates at all, which a lot of times you don't want to allow duplicates. You just don't allow duplicates. So for example, if you're building a set, it's common to build sets out of trees. or hash maps, but we're not talking about hash maps until 250. But you can build sets out of trees, and then the tree is going to handle the duplicates by just not allowing duplicates. Or if you're building a key value store, you would have your values of your nodes be the keys, and then another value, which is the actual value of the key value store, and then whenever you insert a key that already exists in the tree, you would replace the value at that node. And you could do that really efficiently with binary search trees, as we're going to discover. So here's the code. This is not the complete code for the binary search tree class. Now you can see the whole code in the repo. We're going to go through all the code that's in there a little bit at a time, but it's too much to fit on one slide. So these methods look like abstract methods in a non-abstract class, in a concrete class. It's not the actual case. It's just I removed the definitions strictly for the slide, just to put on the slide. But we will show the full definitions of insert and find throughout this lecture. It'll just take some time, and each one of these methods almost takes up a whole slide on its own. But all that code would be in this one class, and you can see how that works in the repo if you check out the code in there. Also, comparator, I'm going to talk about this on the next slide, but this is how we would build a binary search tree. We're going to have a reference to a binary tree node like we saw on Monday. We'll have a reference to that node. That's going to be the root of our binary search tree. And then our binary search tree class, its job is to enforce that property of binary search trees and also work with the assumption that you have that property satisfied. So whenever we insert, we need to make sure that we put the new value in a spot that's going to satisfy the everything to the left less than, everything to the right greater than property. And when we find, we're going to take advantage of that property. We're going to say, well, if everything to the left is less and everything to the right is greater than, let's take advantage of that when we're looking for something, because we can really quickly find what we're looking for in this tree if that property is satisfied. So for this comparator, we're going to sprinkle in some OOP. So I'm going to have a comparator that I create, and I'm throwing something a little bit different at you. This is a trait. I'll circle back around to this, but you can think of this as an abstract class. I just want to show you something new, because we've talked about OOP for 3 weeks. I want to show you something different if we're going to revisit OOP. So I'm going to create a comparator which takes a type parameter, which has one abstract method, compare, which takes two values of the type parameter and returns a Boolean. This is going to be similar to the comparators that you saw in 115. If you took 115 here, where in JavaScript you would have that comparator that would take two values, and I think JavaScript returned an int instead of a Boolean, so I think it was a little different. I don't recall at the top of my head. But we're going to return a Boolean that compares these two values and will return true if the first parameter should come before the second parameter and false otherwise. And this is all the information that we need out of our comparator to figure out the complete sorted order of any data structure full of values, any set of values. So if we use the less than comparator here, so I'm going to extend my class. I'm going to give it type int. So the less than comparator is going to compare ints. My two values need to match that type parameter. My type parameter is int, so these are two ints. And then I'm going to return a less than b. If I give it the less than comparator, if I give a data structure the less than comparator and say sort these things, we're going to get increasing order. If we use greater than here, we would get decreasing order. Our highest values would be first, then we go down. So less than comparator is going to give us the standard default comparator that we're used to, just sorting things in increasing order, sorting these integers in increasing order. So trait, this is the one new thing we didn't talk about during the OOP weeks. Trait is just like an abstract class, except it can't have any constructor parameters. It can, of course, have type parameters. I got one right here. But it can't have a constructor. If I got parentheses and some things here, a constructor parameters, can't be a trait, and I'd get an error that says, yo, make this an abstract class. It can't be a trait. You can't have constructor parameters. The advantage of traits is that you can extend multiple traits. I'm only going to extend one, so I'm not taking advantage of that property. But if you wanted multiple traits, I would extend something and then say with, and then a comma-separated list of additional traits to extend. And in Scala, in the world of Scala, those are called mixins. You get to add extra inheritance through mixins. But those have to be traits. They can't be abstract classes. So if you define something, so if you don't need a constructor parameter, it's common to define your abstract class as a trait to leave your options open, even though, like right here, I'm not taking advantage of that, but it leaves my options open down the road. If I don't need constructor parameters, why not make it a trait? So I have that option later on, which is generally a good idea in programming. You want to keep your options open down the road. You don't want to make a design decision that's going to restrict you to a specific way of coding. Keep your options as open as possible. It's just generally a good way to code things. So when I want to use this comparator, when I create my binary search tree, which takes a comparator, I'm going to create a new object of that type of my comparator, and then my binary search tree is going to order these elements based on that comparator. Again, we're sticking with just ints and less than, so we can focus on binary search trees. But this would be, if I replace this with some other comparator, I can compare ints in any way possible, or I could compare any values I want in any way possible. It gives us maximum flexibility in how we use binary search trees. Binary search trees can be used with any value, with any ordering. So I insert all these values. I want to find a value. Our find method is going to return the node at that value. So when I inserted 4, whichever binary tree node was created to store the value 4, find should return that entire node. So A means, so like when you create a Scala list, you'd say I want a list of doubles, I want a list of strings, I want a list of ints. When you create a list, you're giving it what's called a type parameter. You say, give me a list, and then you specify int like this. You're saying, I want a list that can store ints. I want a map that can store strings to doubles. You give these type parameters to your data structures when you create them. Now that we're creating our own data structures, we need to give anybody using these data structures that same power, that same ability to be able to specify what type you want to store in these data structures. And we do that through type parameters. So the other side of that, like with Scala lists, when we're maps, arrays, we don't get to see the other side of how that works. The other side of how that works is specifying your type parameter list before your regular parameter list that takes values. You specify your type parameter list, then when you use this class, you're going to specify that type parameter. Like here, int, I say int. Now, wherever I have an A, that A is going to be replaced by int. So if I have a binary search tree of int like this, then insert takes an int, and I'm giving it ints. Find takes an int and returns a binary tree node of int. So I give it an int, and I expect node. I should have put my type right here. Right here and here, I missed a couple types. But node is going to be a binary tree node of int. So whenever I create my binary search tree, specify the type parameter, all the A's are replaced by that type. If I want a binary search tree that stores strings, I would give it a type parameter of strings, and all those A's would be replaced by string. Gives us maximum flexibility in our data structures. All right, let's find things. We're going to do find first and then insert. So if I want to find a value in a binary search tree, I'm going to take advantage of the property of left less, right greater than. I'm going to take advantage of that property to be able to quickly find whatever I'm looking for. So to implement this, we have our root, of course, and hopefully we have some values in here. But it could be null. I could have an empty tree that I'm trying to find something in. And to find, we want, when people call our find method, our public API, the way people are going to interact with this code, we want them to just call find and give it the thing they're trying to find. Just like if you have a data structure in any language, you have some data structure and you want to find some value, you want to just give it the value you want to find. But for our recursion, we're going to set up recursion here. For our recursion, we would like a second parameter. We would like to know which node we're currently visiting. And we're setting this up a little bit different than we did with linked lists. With linked list, we created the methods that we created were methods of the node, the linked list node class. So we had a reference to the node we were visiting through the keyword this. We would say this, and that would be a reference to the calling object, which happened to be the node we were visiting. And then we always called each recursive method call was called through the next node, and then we had a reference to next because it was in this. Here we're doing things a little bit different to show you another strategy of how to do that. Instead of creating all these methods in the binary tree node class, we're creating these methods in the binary search tree class because this is binary search tree specific. It has nothing to do with the generic binary tree node. So we're going to write this method to take as a parameter the node that we're currently visiting. And then instead of accessing this dot, we're going to access this node to be able to get the information of the node we're currently visiting. And we did the same thing with our traversals as well. So with this reference of a node as a second parameter, if that's the way we want to set it up, we don't want to give that node up here because then anybody calling this method is going to have to specify that second argument, which doesn't make sense to the person calling this method. Doesn't make sense to them at all. If you want to find something in a data structure, like you don't want to be like, oh, I have to give you a binary tree node of type A. I don't know what you're getting at. What do you want from me? You got to read some documentation to figure out what you need to specify for that. So the public API is just find this value, and then we're immediately going to go to our helper method, which sets up our recursion and our parameter list the way we want, just immediately defers to that helper method that's set up the way we want, but our public method is going to be set up the way the user wants. So this is how we can do that. We just defer to our helper method immediately and specify where we want to start the search, which is going to be the root of the tree. So we start at the root. If it's null, if we have an empty binary tree, we just return null. And returning null is going to be our way of saying the value you're looking for is not in this tree. Sorry, it's just not here. We don't have the value you're looking for. If the node we're currently visiting, which starts at the root, is not null, we're going to ask our comparator, and I always get this backwards. I got it backwards in the other lecture. I'm going to try to do this right now. I'm going to ask the comparator, does the value we're looking for, A, come before the value at the node we're currently visiting, the node's value? If the value A comes before the node that we're currently visiting, then we're going to move to the left subtree. So if the value we're looking for comes before the node's value, based on the property of a binary search tree, we know that everything that comes before the node we're visiting must be in the left subtree of that node. It has to be. So we're going to move to the left. If the value at the node we're currently visiting comes before A or is less than A, then we know the value we're looking for is over in the right. It has to be in the right subtree because that's how binary search trees work. That's the definition of them. If neither of these are true, then we know that this node contains the value we're looking for. So if I have a value I'm looking for and a value at a node, and I say, is this value less than this value? And the answer is no. And then I switch them around and say, is this value less than this value? And the answer is still no. Well, I know these values must be equal to each other. The only way I could get that is if I have two values that are the same. If I have 15 and 15, is 15 less than 15? No. Is 15 less than 15? No. Well, they must be the same. They're both the same value. So if both of these return false, by calling my comparator twice with the arguments switched, then I know that this node has the value I'm looking for. Because this node is equivalent to the value I'm looking for according to the comparator of my tree. Let's find the value 4 in this tree. First, I'm going to ask, is the value I'm looking for less than, well, we start at the root, of course. Is the value I'm looking for less than the value at the node I'm currently visiting? The answer is yes in this case, so I'm going to move to the left. 4 is less than 5. Every single value in this tree that's less than 5 has to be in the left subtree. So we're going to move over here to this node, to the left child, and we've already immediately ruled out all of these values. Because if the value we're looking for is less than 5, and everything over here is greater than 5, the value I'm looking for cannot be in the right subtree. Can't be there. So we just cut our entire search space in half. We're visiting this node. Our search space is 7. We have 7 nodes to look at. We're about to rule out this node, so we have 6 left. And then we move to the left and cut our search space down to 3. Cut our search space in half. If we start with 1 million nodes, like in the 20 questions game, we start with 1 million nodes, and we ask yes or no, and we move to the right or left, we just cut our search space down to 500,000 nodes. We ask one more question, we cut our search space down to 250,000 nodes. Same thing with binary search trees. If I have 1 million integers in this tree, I ask one question: is 4 less than 5? Constant amount of work, just one Boolean logical comparison. And I cut down my search space in half. If there's 1 million elements over here, or 500,000 elements over here and 500,000 elements over here, I just ruled out 500,000 elements with almost no work. I'm going to rule out 250,000, 1/8 of a million, and eventually I'm going to get down to just one element that it could possibly be. In this example of 1 million, I'm going to get there in 20 steps. That's all it's going to take is 20 comparisons. 20, hey, is 4 less than 5? And I'm going to get down to the value I'm looking for. Extremely efficient. Extremely efficient. As opposed to looking at every single value of 1 million values, we're looking at 20 of them. At this node, is 4 less than 2 is going to be false. So we're going to check, is 2 less than 4, or the way I have it written, 4 greater than 2. We're going to move to the right because the value we're looking for is greater than the node that we're currently visiting. So we're going to move to the right, and we're going to check, is 4 less than 4? It's false, so we're not going to the left subtree. Switch the parameters, or switch the arguments. Is 4 less than 4? False, so we're not going to the right subtree. Well, there's only one option left. The value we're looking for must be at this node, so we're going to return a reference to this node because we found what we're looking for. Now suppose we did the same thing, but we're looking for the value 12. We're going to start here. 12 greater than 5, move to the right. 12 greater than 8, move to the right. 12 less than 14, move to the left. We get null, so we're going to return null all the way up and say, hey, sorry, 12 is not in this tree. Okay, insert, a little bit more going on here. Why can't 4 be stored to the left of 8? So why can't this be 4? Because at this node, we would break the property of everything to the right subtree is greater than 5. So we cannot have 4 anywhere in that right subtree. So we can't insert 4 here. All right, so our insert method, the last method that we want to talk about with binary search trees, is a little bit more going on, but not overly so, not too much. Is we want to do the same thing. We have our method that we expose to the user. The user just wants to give us a value and tell us to insert it. But in our recursion, we want to navigate the tree, so we're going to store a reference to the node that we're currently visiting as an extra parameter to our recursive helper. So we're going to call that helper and start at the root. With one caveat, if the root is null, so if I have no values in this tree, there's no decision to be made. The value that's being added is the root. It's the first value that's been added to this tree. There's only one place to put it. It's the root. So set the root equal to that, and there's no recursion to be had. We're just going to set that value as the root. Otherwise, if I already have a root, we're going to go to our recursion. we're going to call our comparator and say, is the node's value that I'm looking at, that I'm currently visiting, less than, or does it come before the value that I'm inserting? If the answer is yes, we're going to go to the right subtree. So if the value, another way of saying this, is the value I'm adding greater than the node that I'm looking at, move to the right. If the right child is null, then I've found a home for this value I'm adding, and I'm going to insert it right there. I'm going to set the right child that's currently null to a new node containing the value that I'm inserting. I've inserted that value into the tree, and I'm done. If the right child is not null, we're going to make our recursive call. We're going to call insert helper with the same value. We're still inserting the same value, but we're going to make a recursive call to the right, so node is now going to move to the right child of the current node that we're looking at. If this comparator returns false, we're going to move to the left subtree, so my ties are going to be broken to the left. I'm not going to add any duplicates, and I won't do it to you on the quiz either, but if I were to add a duplicate, like my code has to handle that situation. If I were to add a duplicate, it would go to the left subtree. I'm going to break ties to the left for what it's worth. If the left child is null, I found a home for this new value, else recursive call and move on to the left subtree. Visually, if I have this tree that we've been working with, but before we have 7 in here and we want to add 7, I'm going to check, is 7 greater than 5, or rather is 5 less than 7? We're going to move to the right, because everything greater than this node's value has to be in its right subtree. 7 is less than 8. Everything that's less than 8 has to be in its left subtree. And its left child is null, so we don't have to make another recursive call. We've found the home for 7, and we're going to insert 7 in a new node right there as the left child of 8. And all the recursive calls return. All right, so that's insert. So we did find, insert. Those are the two methods we want to talk about. And now that we have our binary search trees with this property, and we saw this last time, we foreshadowed this a little bit. This tree was very carefully chosen in Monday's lecture to be a binary search tree, and I did an in-order traversal. One nice property that we get from binary search trees when we do an in-order traversal is that all the values are visited in sorted order. This makes in-order traversals on binary search trees very useful. So an in-order traversal is going to make a recursive call to the left, visit everything in the left subtree of that node, then visit this node's value, then make a recursive call and visit everything in the right subtree. And that's true for every node. And based on our definition of a binary search tree, we know that if we visit everything in the left first, well, that's everything that's less than the node's value, and true for each node. We're going to visit everything less than that node's value, then visit that node's value, then visit everything greater than that node's value. And we do that for, okay, that returns 5 just visited everything less than it, then visits everything greater than it. Well, if that's how we're doing our traversal, just based on the property of a binary search tree, we have to visit these nodes in sorted order. And that's the main advantage of a binary search tree, is that we're maintaining order in our tree and also being efficient about it. So if this binary search tree is balanced, and by balanced I mean for each node in the tree, the number of nodes in its left subtree is equal to the number of nodes in its right subtree. So if it's balanced, or at least close to balanced, we have some really nice properties here. The height of the tree is going to be O of log n, which means the distance, if I start at the root and I keep navigating left, right, etc., to get to nulls is going to take me O of log n steps. I'll follow that many references, which is very low, as we saw with the 20 questions example. If I have 1 million nodes, my height is going to be 20. Log n is very, very powerful in computer science. It's very, very efficient. If I have 1 billion nodes in my tree, log base 2 of 1 billion, still only 30. This is very, very efficient. So if I have a binary search tree and I just insert n elements and then do an in-order traversal, this is a new way to be able to sort in n log n. As long as we can insert in log n time, which our insert method is an O of log n if the tree is balanced. We have a new way of sorting in n log n, which is the fastest that we can possibly sort asymptotically. So we have another asymptotically optimal sorting algorithm just by default. And the big thing with a binary search tree is that it maintains sorted order even on dynamic data in log n time. So every time a piece of data updates, or you insert data, or you delete, we didn't talk about delete, all those operations can happen in log n time. So if you have a very large data structure that needs to stay sorted and the values are constantly changing, binary search tree is your savior for that. I always think of a leaderboard. If I have millions of players in my game and I have a global leaderboard, so the players are constantly updating their top scores, new players are added to the game, I'm thinking binary search tree for that. So all these changes can be done in log n time while maintaining a sorted order of the overall leaderboard. We can't do this. We weren't able to do this before with an array. The inserts take linear time. Linked list, insert is O of 1, but to find the location to insert is O of n. So for example, if you want to insert to the end of a linked list, you got to navigate the whole linked list first to just get to that location. So this is the first time we have that feature. But wait, what if the tree's not balanced? The tree that I showed you will not be efficient all the time. So what if I insert values in sorted order? So I insert -3, I insert 2, well that's greater than -3, I insert 4, greater than -3, greater than 2. We're constantly going to the right to insert our values. And we basically end up with a linked list and we have O of n insert, O of n find. Everything's really inefficient with this. So how would we insert and delete from a binary search tree in log n time while maintaining the balanced structure of a binary search tree? Well, I'm going to leave that question for 250. They'll answer that in very much detail. This is actually possible. You can insert, delete in log n while maintaining the balanced structure of a tree. We call them self-balancing binary search trees. And when we actually use binary search trees, we're using self-balancing binary search trees. Really, really nice data structures. Implementation, but I'm pushing up against it here. Have a great day. I'll see y'all Friday.